The paper of the day is Optimizing Space Amplification in RocksDB. The paper discusses the optimization of space amplification in RocksDB, a high-performance key-value storage engine developed by Facebook. The focus is on enhancing space efficiency while maintaining acceptable read and write latencies. The authors present various techniques to reduce storage usage, such as dynamic LSM tree level adjustments, tiered compression, and shared compression dictionaries. The paper demonstrates that RocksDB uses significantly less storage than InnoDB while maintaining competitive performance, especially in OLTP workloads. Here are the key contributions. In terms of space efficiency, RocksDB achieves less than half the storage usage of InnoDB by employing log structure merge trees and various compression techniques. Performance trade-offs. The paper explores the trade-offs between space efficiency, CPU overhead, and read-write amplification, showing that RocksDB can maintain high transaction throughput with marginally increased read latency. Third is innovative techniques like introduction of novel techniques such as dynamic LSM tree, level size adjustments, and tiered compression to optimize space amplification. In terms of highlights, there are three key ones. The first is the storage reduction. RocksDB reduces storage space requirements by 50% compared to InnoDB, enabling significant hardware consolidation. Second is transaction throughput. Despite the focus on space efficiency, RocksDB achieves higher transaction throughput than InnoDB and TokuDB. Third is compression strategies. The use of tiered compression and shared compression dictionaries significantly enhances space efficiency without severely impacting performance. Here are the key figures. The first figure is which illustrates the SSD file organization in RocksDB, highlighting the structure of LSM trees. As you can see in the figure, each level maintains a set of SSD files. Each SSD file consists of unaligned 16 KB blocks with an index block identifying other blocks within the SSD. Level 0 is treated differently in that its SSD files have overlapping key ranges, while SSD files at the other levels have non-overlapping key ranges. A manifest file maintains the list of all SSD files and their key ranges to assist lookups. Here's the second one, which depicts the compaction process, which is crucial for maintaining space efficiency. The contents of the selected level I SSD file is merged with those SSD files at level I+1 that have key ranges overlapping with the key ranges of the level I-1 SSD. The shaded SSD files in the top part of the figure are deleted after the merge process. The shaded SSD files in the bottom part of the figure are new files created from the compaction process. The compaction process removes data that has become obsolete, that is the data that has been marked as deleted, and data that has been overwritten, that is if they are no longer needed for snapshots. Here is a key quote. RocksDB uses less than half the storage than InnoDB uses, yet performs well, in many cases even better than P243-based InnoDB storage engine. Overall, the paper gets 9 out of 10 for its comprehensive approach to optimizing space amplification in a widely used storage engine, its innovative techniques, and its practical implications for large-scale data storage systems.